right. So what we're going to do is we're going to do new material, and it's kind of related to what we've been talking about. You'll see. Uh, this Chem 122 is really more in terms of what happens. Um, it's called physical chemistry, and a lot of times it doesn't really matter who's in play, what chemicals are in play, etc. It's how it's a way of measuring, like we did with kinetics, measuring speed, gas particles. Um, I guess we didn't cover gases. That was 121, but mixtures, uh, etc. And uh, so we're going to continue with this looking at what you might call physical chemistry, which is kind of looking at like the physics of chemistry, though we don't really go into a whole lot of that. But it's along those lines. Okay, so pay attention as we go along here, and there's going to be some new concepts, and they're going to and there's going to be new kinds of problem solving. So the first, there's going to be two videos here. The first one is going to cover the basics of chemical equilibrium, and more along the theory behind it, and then the second one will cover more practical problems. Okay, dynamic equilibrium in a chemical system. All right, chemical equilibrium exists when the rate of the forward and reverse reactions are equal. So what we're going to do is look at that is that if you had a reaction A going to B, that's and doesn't matter if it's sexual or endothermic reaction at this time. Usually, we just assume that the chemical reaction will move from A to B, but in reality, the reaction can go back to A as well. All right, and the way that you can make sure you can test this and see that it happens is if you have a completely closed system, isolated system, and that way you can keep A and B together without any energy and matter leaving. And what you'll see is that A is start making B, and B will start going back to making A. Now, in the long run, when you get all done, you might have like 1,000 B's, and you might only have 25 A's. And when you look at the system, you see that there's 25 A's and there's 1,000 B's. So it looks like it's static. But actually what's happening is that A, it might be making 5 B's, but at the same per second. And then, but going back the other way, there might be 5 B's going to A's. And so what you have here is the rate of the forward reaction is equal to the rate of the reverse reaction. So it's dynamic, all right? Now, getting to this point, so if you started out with 1,500 of these and 0 of these, the reaction we'll see is that if it prefers to make product, the reaction will start to dump and make a lot more product than leaving a reactant. So it's going to eventually get to the 1,000. Okay, but once it gets to 1,000, it can't go past that unless there's something that changes, takes some of this out, or messes around with this number, or messes around with this number. So this ratio here is going to be constant for this reaction, as well as the rates. Okay. So the reaction appears to stop, but it doesn't. But it remains constant. All right. So even though it's moving, the forward and reverse reaction never cease to exist. And so what we do is we end up drawing a double arrow, okay, to represent this process of moving back and forth. Now, so all chemical reactions will reach if you let them sit long enough and there's no uh, and there's no disturbance to the system, will come to equilibrium. All right, so we'll get into that as well. Okay, so initially we have just our dinitrogen tetroxide, and the reaction is only forward when we begin it. And as the reacts form the product, and as the product gets formed, the reverse reaction starts to take place. Okay. And they start colliding in each other, and there's more and more particles, just like we talked about in kinetics. And the rate of the formation of this starts to increase, while the rate of this guy actually decreases because there's less of it. And then eventually we get to equilibrium where the concentration of both of them stay the same. Okay. Right, so here's sort of a diagram what happens. So here's your starting point of the N2O4, and what happens is it starts to make product. Okay, and the product starts to form, and there's more and more of the product, and what it's going to do is that because there's more product, rate is going to increase because rate is dependent on concentration, and this rate's going to decrease because again rate is dependent on concentration. So this guy goes down and this guy goes up, but at some point this is that they just kind of just make enough of each other. All right, so this guy will start producing this, and this guy will start making this. And then when that happens, it's at equilibrium. Where the equilibrium lies depends on the system. Some systems equilibriums are hard to detect. Okay, that's because maybe there's almost all of the A may go to B. So, if you start out with 1,000, 1,000 of these A's at the beginning, when you all get done, there might be only one of these left over and 999, and so it'd be hard to detect that you've actually have any A. Okay, reaction reversibility, isolated system. So no energy can leave, and no matter can leave. It can be reached, the equilibrium can be reached either direction, independent of whether it starts with the reactant or product. So you can start out with product actually, and then the reaction would go to the reactants, and then I come back and forth. Okay. Okay, so let's say, for a given overall system composition, always reach same equilibrium concentrations, whether equilibrium is approached from the forward or reverse reaction. So let's say you started out with just your product, okay, 0.07 moles in 1 liter. What's going to happen is that this will start making the reactant, and then they'll start forming, and then they'll go back and forth until they hit their amounts that are set for equilibrium. So you could start out with product and go to reactant, or you could go from reactant to product. It really doesn't matter where you start, as it'll always reach equilibrium if you have an isolated system. Right, simple relationship between reactants and products for any chemical system at equilibrium, called the mass action expression, derived from thermodynamics, which we're not going to cover a whole lot. But we have a forward reaction. I'm going to go into a little bit. So forward reaction is A to B, reverse is B to A, and at equilibrium they're A, B, B to A. So let's just talk about what happens. So an equation, here's the equation at equilibrium, where A is the coefficient and A is the reactant, B coefficient, and B is product. The forward rate is rate F equals KF to the A, and we're leaving the exponent off for now. And then the reverse rate is R rate equals KRB. Okay, leave that. And then at equilibrium, we'll say the rate forward is equal to rate reverse. And so we have this relationship. Okay. So the rate law of both forward and reverse reaction are equal. Right, now if we just do a simple math and get the K's on the same side, so what we're going to do is divide both sides by KR and both sides by A. We get this relationship. All right, and a constant divided by a constant is a constant, and we're going to call that the equilibrium constant, K, big K. And so what we got here is big K is equal to the product, B, over the reactant, A. Now, what happens is that because of all the particles smashing into each other, which is dependent on the amount of particles, this is that what we're going to do is actually include the coefficients into the equations. Okay. So the equilibrium constant for this reaction would be, so K, the equilibrium constant, is equal to concentration of B to its coefficient divided by A to its kind of coefficient. And so this is be the basic way that we'll write equilibrium expressions. Okay, with product over reactants. Okay, now another important thing about to look at reactions is that not all chemical reactions are at equilibrium, and so what we would like to do is also be able to measure the relationship of the product to the reactant at any given time. And so if we had a reaction A plus B, okay, with their appropriate coefficients going to CC plus DD, okay, maybe when we first start the reaction, let's say we just had reactant, it's not going to be at equilibrium, but we would still like to measure the ratio of our product to reactant. So let's just take a quick look at this as in terms of this chemical equation. This thing is called the reaction quotient, Q, and it's the ratio of product to reactant at any given time. Now K is a special case of Q, and then that's when it's at equilibrium. But let's just take a quick look at this Q. All right. So let's say you just start out, there's no product yet. What would Q be equal to? Right, so if there's no product, Q is going to equal to 0 over 1. Okay, so Q is going to be a really low number. Okay. Okay, virtually, if there's practically 0 of it. Okay. Okay. Now, so it's going to be lower than equilibrium, in fact. Okay. So if, let's, because there is no. So if you have less, if your product is low compared there to its equilibrium value, Q will be less than K. All right, if there's not enough product. Okay, and we're going to go into this more, okay, to reach equilibrium. Okay. Now, so if you don't have a lot of product, the Q is going to be less than K. All right, and we're going to see is the reaction is going to want to adjust Q to get to K. All right, so it's going to make more product. Now, if you go it the other way around, let's say there's not very much reactant. All right, so we won't go to zero. So it's not much reactant. Okay, this case Q compared to product, Q, let's say it may be like 1,000. So the product to reactant's 1,000 over 1. Okay, let's say it's not at equilibrium. You can see that Q is very large. Okay, so when Q is large, okay, it's going to be, if Q is greater than K, that means there's not enough reactant. Okay, all right, and this will come into play when we study these problems more. Okay, so Q is going to be an important thing to take into account as well when we look at our problems. Okay, equilibrium law. For a reaction, H2 plus I2 gives me 2HI. So what I want to do is I want to write the equilibrium expression. So the reactive product goes on top, and the coefficient gives the power. And the reactant goes on the bottom. Okay. All right. And the 49.5 is a given value that was found experimentally. Notice it has no units. The units will cancel out. Both of these are molar. So this molar squared, this molar, and this molar, so they cancel out. Equilibrium constant, we call this Kc because it relates to concentration. We're just looking at the concentrations. Okay, for equilibrium expression to exist in reaction, the Q must equal to Kc. All right. Okay, so this shows what we've been talking about. So here's a general chemical reaction here. So here's general chemical reaction. So it's going to be products over reactant, where the coefficients are the exponents. And so the equilibrium law for this, since we're talking about concentrations, Kc is equal to F G times G over D times E. Okay, so this shows you the same thing. We have products over reactant. Keep this. I mean, this is. I always like to think of this relation as product over reactants. All right. So let's look at a problem here. So here's chemical reaction. We're given that, and we're given that the equilibrium constant is 4.26 times 10 to the 8th at 25 degrees. So what is equilibrium law? It's simply this: product over reactant. Don't forget the exponents here, and then here's your number that was determined experimentally. Now let's just take a look at this number. Just putting numbers up here is worthless unless you understand it. So what this basically says is that this is product up here and this is reactant. So you kind of can think of this is that this is 4.26 times 10 to the 8th over 1. Okay, so that means there's a lot more product than a reactant. Okay. So keep that in mind. These numbers aren't just numbers. It gives you an idea that this reaction really favors the product. Okay. So if you looked at this reaction, you wouldn't even hardly notice that there was any reactants. Okay, because this is a huge number. Okay. Now if this was 10 to the minus eighth. Okay. So if let's say if it was 10 to the minus eighth instead, okay, that's basically saying 1 over 10 to the eighth, and that means there'd be more reactant than product. Okay, so if you get a number so if this exponent is positive, there's going to be more product and reactant, and if it's a negative exponent, there's going to be more reactant than product. This essentially says that for there's 100 million reactants for only one product. So think about the numbers in terms of what they really mean as well. Now, there's important people that you have to know. You don't have to know them, but I just want to make sure you know that you're actually paying attention to these slides. And so I'm going to throw this thing in right now. So there's this woman named Kizzmekia Corbett, and she has nothing to do with equilibrium law, but she's an African American woman in her mid-30s, I believe, that was involved with the discovery of the protein, the spike protein for the coronavirus. All right, so there might be a little question on the quiz about her. Just want to make sure you're listening to these. Okay, write the mass action expression for the following. All right, so this means Q. So the reaction quotient we're basically asking. So write the reaction quotient for this expression. Okay, here you go. There we go. Now do it for this reaction. Okay, and you'll see it looks just like the equilibrium constant, but Q is a general statement for any time, even at non-equilibrium. Okay, so let's take a look at this one. So write the reaction quotient or mass action expression for it. Again, it's going to be product over reactant. So all of these have product over reactant. So we have to make sure the reactant has the ammonia to the fourth power, and it's A. Okay, so here's the way to write the equilibrium expression for this guy right here. If you were to flip it, so you have the product here, the reaction would look like this, which you see is the inverse of the original way we wrote it. Okay, and that makes sense. So this is that if you have the ratios 10 to the 8th, if your K is 10 to the 8th here, going the other way would be 10 to the minus 8th. Okay. Okay, and this just shows that. Okay, so if this is your the reaction that we gave a few slides back, we came up with this. But if you would look at the reverse reaction, there's going to be so this says we have a lot of product, okay, and we went over is that the reverse reaction says you have a lot that you don't have a lot of reactant when you're all done. So if you look at the reverse reaction, there's going to be not much of this compared to this. So the reactant, so the product, very small amount, and the reactant, very large amount. Okay. Again, I said if this number here is positive, that means you have a lot of product. Okay. Whoosh. So product outweighs reactant. Now, if this is a negative number, that means reactant's going to outweigh the amount of product. Okay, so here's just another way to explode more about what's going on. So here's our reaction. Now we put coefficients in front of it, and so now it starts out as this expression here, but you could think about it being done 3 times, or you can think about it as the coefficients being on power, and either way, is that the relationship between this guy and this guy is to the 3rd power. All right, this just looks at the previous reaction. So now what we're going to do is multiply the coefficients by 3. Okay, so what we're going to do is have 3 times as much product and reactant, and therefore our equilibrium is going to go up by the power to the cube. All right, so notice this is that it's not linear. This is as you increase your amounts, it actually goes up exponentially, and that has to do with more and more particles being able to hit each other because there's more particles. So this is just a way of finagling and messing around with the equilibrium constants. Okay, and how they relate to each other. And here's just another example. So if you take, here we have 2 chemical reactions, and we put the 2 chemical reactions together. So if you add these 2 together, you'll get this guy right here. And basically these are just, so when you add the 2 reactions, you multiply the equilibrium expressions. And when you do that, you end up getting, okay, these, so just cancel out with this. And so you end up with DFG times ABE. All right, so it's going to be DF and G, which is DF and G, all over A times BE, which is essentially this times this. All right. All right. And this shows you an example of it. So we have 2 reactions here. Okay. You add the 2 reactions, so you get 2NO2 plus NO3 plus CO gives me NO3 plus NO and O2 plus CO, and this ends up being the resultant. So if you remember Hess's law in 121, that's sort of what we're doing here. So you have your 2 equilibrium constants. You don't add them together. You end up multiplying them together. And so this guy is a product of these 2 guys together, right? This guy right here, and this guy right here. Okay, when you multiply those together, you get this guy. So, our resultant, right, is equal to our product of our 2 reactions. Okay, so we saw similar type things with Hess's law. So when you add the 2 chemical reactions, you end up with the resultant reaction, and then you will multiply the equilibrium expressions to come up with the summative product of the final equation. All right, so here's another problem. Let's say we start with N2 plus 3H2 gives me 2NH3. And I know the Kc is 500. What would be the Kc in the reverse reaction? Okay, so it's going to be the inverse of our 500. So it's simply 1 over 500, or 0.002. Okay, now if we decide to take original equation and divide all the coefficients by 2, that's essentially taking the square root of our initial and coming over 22.4. Equilibrium constant Kc, that's what we've been talking about. Right. So, but sometimes we want to measure not the concentration. We might want to measure partial pressure, especially if it's if we're measuring if we're looking at a chemical reaction that just involves gases. And so you could write the equilibrium constant in terms of Kp, and then you could write it simply as the pressure. So same thing is that so you have to include the coefficient. Notice there's no brackets here, so it's going to be pressure of NH3 squared over the reactant, which is N2, pressure of N2, times the pressure of H2 to the third power, because there's 3. So here's the equilibrium expression of this reaction if we're just looking at the partial pressures of each gas. So how are Kp and Kc related? So we know they are related because we have the ideal gas law, which says pressure and volume are related to each other. If we rearrange the equation, we get pressure is related to nRT over V, where NV, moles per liter, is molarity. And we saw a similar expression when we talk about osmotic pressure. And then substituting PR into the Kc reaction. So what we're going to do is replace the pressure with this right here, and the moles gas in the product. We get the relationship of the equilibrium of pressure is equal to the equilibrium constant concentration times RT raised to the N. So, and we'll have to really be to change an N, and that's sort of one of the key things in this equation. All right, that affects it a lot. All right. Okay, so consider reaction N2N2 gas and N2O4 gas. We know what the Kp is, and we found that experimentally. What is the value of Kc at the same temperature? So we're going to use this equation here, and we have to pay attention to this over here, change in N. Well, change in N is the number of products, the product number minus the reactant number, moles, in terms of the coefficient. So if you look at this reaction, it goes, the product, there's only one, is that the ratio is 2 to 1 moles. So there's only 1 mole product for every 2 moles of reactant. So the change in N is going to be 1 minus 2, or minus 1. So we're going to end up putting the minus 1 over here. And what we want to do is solve for Kc. So rearrange the equation for Kc. And we get Kc is equal to Kp over RT raised to the minus 1 power. 0.48 is what we're given. We're leaving the units off here, but this would be it'll all work out. Okay, it says uh, sometimes we just sort of skip over the units, but so this is 0.0821 liters per atmosphere, moles per Kelvin, and so it's this times 298, which is 25 plus 273, and do this math, and you end up getting the equilibrium constant at 298 is 11.7 equilibrium for concentration. All right, try another one of these. So here's our equation. The N goes from, so a product, so there's 2 of the product, and there's 4 of the reactant. There's a 1 in front of the N, and there's 3 here, so product minus reactant, so the minus 2 is the change. So okay, then we just do the math, and we come up with, sorry, this should be a Kc right here, and a Kc. All right, so Kc equals 41 divided by RT to the minus 2 power, and Kc equals 4.42 times 10 to the 4th. Right, here's another one. So the change of N is going to be 4 minus 3. So there's 1 here and a 2. So it's 4 minus 2 minus 1 is 1. Kp is equal, here's our equation. We plug everything in. This is a 1 over here. 25 is 298. I plug everything in, and Kp is 24. All right, homogeneous reaction at equilibrium. All reactants and products are at the same phase, and that's usually what we like to do. We like to have chemical reactions at homogeneous reactions so that we can measure all the products and reactants are in the same phase, and we can use them in our equilibrium expression. If they're not in the same phase, then we may have a problem in actually measuring their equilibrium, because if you have one in a liquid and another one in gas, it's hard to write that as a concentration or a pressure relationship. Right, we're going to look at a couple of examples of heterogeneous. So we have this sodium bicarbonate is a solid, and it goes into sodium carbonate plus water and carbon dioxide. Now you can write an equilibrium expression for this, right? But it's not going to just be concentration or pressure. So you can write product. It's going to say product over reactant. Here's your product over your reactant. Okay. You can write it in a simpler form, and the part of it is that the really the solids are going to kind of just turn out to be a constant. Okay. So what we can do is rewrite the equilibrium expression as the concentration. Equilibrium of concentration is equal to our original equilibrium expression times our solids, because this ratio is going to be constant. Okay, and so it's simply going to be equal to our two phase, our water and carbon dioxide that are in the same phase. So equilibrium law for heterogeneous systems written without concentrations of pure solids or liquids. So we typically just sort of cancel these guys out, because they're not going to have that big of an effect on changing the concentrations. First of these guys, because it's gases and liquids, they have a lot more. They take a lot more volume up than the solids. So if you have, basically it's saying if you have 10 more of this solid and 50 more of this solid, you're hardly going to be able to tell because they're densely packed, and so you can kind of just leave them out. All right, so write the equilibrium count law for this reaction. Okay, so we're gonna leave this guy out because it essentially stays constant. So it's gonna be so densely packed. So if you add 100 more to something that's already, so it's 500 and you add 100 more, it's really not going to change the concentration of it a whole lot. Okay, but these guys, because the particles spread out more, the volume changes. So it's essentially we'll cancel it out, and we'll end up getting the product, which we're going to say is 1 over our reactant. Okay, and we're going to be using this type of reaction when we get into solubility. Right, again, if we look at this reaction here, we can cancel out the water because the particles are densely packed, and so it's just simply going to be these two guys over our reactant right here. And this is also going to be important when we get to acids and bases. We're going to see this type of reaction used often. All right, so let's take a look at, we have this calcium plus phosphate gives me calcium phosphate. We can ignore, not totally, but we can ignore it and we can just call it 1. So it's just going to be simply product, which is 1 over our reactant, so it's D. And again, this is Q, not K, but it doesn't matter. K would be equal, have the same ratio. So this would be given the reaction, what is the expression, the reverse reaction? So now you're looking at this direction, so it's going to be, these guys will be on the numerator, and a 1 would be on the bottom, and so you can see that this would be B. All right, so let's go back and actually try to understand more about physically what K represents. So if K is and I talked about this earlier, so if K is very, very large, all right, so if your exponent is greater than 1, that means there's going to be a lot of product, and we say it's rich in product. Okay, and that means reaction is going to move from left to right. That's where it's going to favor. It's going to favor making product. And again, you can think of it as there's this much product to this much reactant. So you can there's a, if you look at these numbers, this basically says there are 10 to 26 products for every one reactant. So you could hardly even tell that there will be any reactants when you're all done. But there still will be if you're at equilibrium. Okay, if K is close to 1, you're near equilibrium. Okay. And again, if K is a lot less than 1, that means you have a lot more reactant product. So this is negative 21. So another way to think is 10 to the minus 1 is like 1 over 10 to the 21st. Okay, so this is product and this is reactant. So at equilibrium, okay, there's a lot more reactant than product. In the previous slide, there was about equal product and reactant. All right, and this is k greater than, much greater than 1. So if you have an exponent, a positive exponent, okay, big positive exponent, that means more product, favors product. Okay, and you have a negative exponent, there's more reactant. Okay, and then you can have where you can have equal, which you don't get this very much, but you can. All right, consider the reaction of 2NO2 to N2O4. So you can see that this is Kp equals 0.48 at 25 degrees. So if you think what that means, right, this is almost 0.5. So you can say, and if you want, you can write it as an exponent. So let's do that. So 4.8 times 10 to the minus first. All right. Okay. So what this is telling me is that there's a lot less. So the ratio is product over reactant. Okay. So this can be written as 1 over 4.8 times 10 to the first. And you can see that there's more reactant than product. Okay. All right. So this reaction would favor, when it gets all said and done, when it gets to equilibrium, there'll be more of the reactant than product. But you can see they're fairly close to each other, so it's not going to be that much different. Okay, now we're going to take a look at the relationship between Q and K. We did go introduce you to this before. All right. So K is a special case of Q when at equilibrium. So when the system is at equilibrium, QR is equal to K. Now, if there's Q is less than K, there'll be reactants will go to product. So let's take a look at what that means. So let's say you have Q. So let's say the equilibrium is 2. Okay. All right, 2 over 1, which means there's, for every product, there's so the reaction favors product. Okay. So let's say that Q is equal to 1. Okay, if it's equal to 1, you can see that that there's not enough product yet. Okay, because it wants to have twice as much product. So if Q is less than K, all right. So what's going to do? The reaction is going to push towards the product. Okay, so when Q is less than K, the reaction will push towards product. And I hope you'll see how that works. So let's say that K is equal to 2 over 1. And the Q is 1 over 1. You can see there's not enough product here to get to equilibrium. So the reaction is going to make more product to get to 2 over 1 ratio. All right. Okay, so, and don't worry about these numbers, but that's what would happen is that there'll be more, and then when you get all done, the ratio will be 2 to 1. Now, if we look at the opposite, where Q is greater than K, so now let's look at the same scenario. So let's say K is equal to 2 over 1. That's product over reactant. Okay, so now let's say Q is equal to 4 over 1. All right. Okay, you can see there's too much product here. Okay, so the equilibrium wants to have 2 to 1, so the reaction is going to start to make more reactant. So it's going to push it towards reactant. So if Q is greater than K, all right, it'll make more reactant. All right, so I could rewrite this one up here as K is greater than Q. It'll push towards product. That's another way of writing this up here. Now, I really would like you to remember why this makes sense. Okay, it's like I explained it. Okay, but I'm gonna come up with a little trick here to help you memorize it. And it's, I don't know if it is politically correct or not. Okay, but it's this way. Somehow I remember it from a long time ago. Is that when K is greater than Q, it goes to the right. Okay, so one way I sort of remember a long time ago is that when kings are greater than queens, everything is right. Okay, it's probably not right politically or as such, but that's just a dumb way to remember it. But it's better to remember the actual reasons and reasoning of it, like I described. And I am going to, as we go through these, I will always try to explain it and what it makes in terms of common sense, not in terms of a silly device. Okay, now this is where we're going to get into something called Le Châtelier's principle. So I said if there's too much Q, I mean if Q is greater than the equilibrium constant, reaction is going to form reactant. So why is that? So what's the deal here? Well, the thing is that all chemical reactions want to come to equilibrium. It has to do with entropy and other things that we probably won't get into a whole lot, all right? But so there is a general principle in chemistry that which we didn't touch on, but we could have earlier. It's called Le Châtelier's principle. Okay, and Le Châtelier's principle says is that if a system is at an equilibrium, and somehow that system gets changed. So let's say you have A going to B, and it's at equilibrium, and all of a sudden you add more A, the reaction is going to get disturbed. And what's going to happen is it's going to push the reaction to the right to make more B to fix the equilibrium. So Le Châtelier's principle is a way of expressing how it's that a system that is not at equilibrium or it's been disturbed will do what it needs to try to get back to relieve that stress and get back to equilibrium. Okay, and we're going to look at different things that can affect the change in equilibrium: concentration, pressure and volume, temperature, catalyst, and adding more gas at a constant volume. Okay, so let's look at this. Want to know what's going to happen with the change in concentration. So I have this chemical reaction here, and what it does is it changes from blue to yellow, and at equilibrium, because you have blue and yellow, it's going to look like blue-green. And then you can write the equilibrium expression as the following. Okay, and we can rewrite it even. We're going to get rid of the water, and then you could write it simply as this. Now, what happens if we add, we're at equilibrium and we add more chlorine? Okay, what's that going to do is now we have more reactant than product, okay? And so the system is going to want to remove some of the reactant and more product. So if you add more of the reactant, it will force it to the right, and it'll become more yellow. So it shift to make more product. Okay, so we're going to see as we go along, we'll get similar type of things. So another way is if you, let's say you added this guy, the reaction would go back to the right. To the left to get back to equilibrium. Another thing you could do. So it's good. We're looking at like a push-pull. So if you add chlorine, it'll push it to the right. Add more copper chloride 4, it'll push it to the left. There is also another effect. Is that let's say we remove this from the reaction somehow. Okay, the reaction is going to move to the right to try to make more of this product. So that's the pull. Okay, so if you add more of a substance, you push it to right or left, and if you take it out, you'll pull the reaction one way or the other, and we'll see examples of that. Okay, so what we're going to do again, we're going to so we have this chemical reaction, and we're going to be kind of fancy about it. What we're going to do is we're going to add some silver to it. Now what the silver does is it's going to pull the chloride out of solution and make silver chloride. All right, so that means the chloride is being removed. So the chemical reaction is going to try to make more chlorine, and so it's going to pull the reaction this way. So it's going to go to the left. Okay, when changing concentrations of reactant products, removing products, okay, removing products will cause the pull, and then adding more product will cause your push. Okay, so if you have A going to B, and you add more A, the reaction will go to the right. This is if you're at equilibrium. Okay. If you take away B, the reaction will also go to the right. Okay. Now, if you add more B, the reaction will go to the left. Or another way to make it go to the left is to take away A. So we have this reaction here, and we're going to add more oxygen to this. So we're going to add more O2, and that's going to push the reaction to the right, or to the products. All right, now let's look at a gas relationship. And what we're going to do is change the volume of our gas. So here's our equilibrium expression in terms of pressure. So we're going to reduce the volume. So if you reduce the volume, pressure is going to go up, Boyle's law. So what you want to do is you want to reduce the pressure, so to stay at equilibrium. Now, so what you do is you look at which side of the reaction is going to reduce the pressure the most. Okay, so look at this. Look at the reactant or product. So the reactant has two particles, and the product has two particles, and the reactant has 4 particles. So the reactant, so if the pressure is going to be really, is going to affect the reactant more than the product, because there's 4 times. And so what the reaction is going to do is it's going to relieve that pressure by making more product. Okay. And so what you do is you look at the number ratio of product particles. Okay. These will increase. So if you reduce the volume, that's going to increase the pressure, and effectively the reactant is going to have a higher increase in its pressure because it has more gas particles. It has 4 to 2. And so I want to relieve that pressure, okay, by making more product. Right, here's another example. Again, let's change it to, so we increase the pressure. Okay, and now if you notice the number of particles are the same, there's 2 particles on each side, 1 plus 1 and 2, and there's 2 over here. Therefore, the pressure on both sides is going to stay the same, and there's not going to be any shift in equilibrium. All right, if you look at this one, this is a heterogeneous mixed equilibrium. We're at equilibrium, and what we do is increase the pressure. So it's going to increase this guy. All right, it's not going to have any effect on these 2 guys. And so the reaction is going to be pushed to the left because there's more pressure on the product side than the reactant. Essentially, there's 1 particle to no particles over here. Now let's look at temperature, how that may affect equilibrium. So let's go back to our equation of our blue going to yellow and yellow back to blue. This reaction is endothermic. All right, and we could measure that. So heat goes over here. Okay, so notice how I wrote the heat. I wrote it as part of the equation. Now it's actually can be considered as part of the equilibrium. So if you change the temperature, essentially heat up, okay, that means you're adding more heat. That means the reaction will go to the right. Okay, now if you were to take away heat, pull it away, the reaction would go to the left. Okay, so if you heated it up, the reaction will go to the right. If you cool it down, it'll move to the left. All right, so this is looking at ice melting and water freezing at equilibrium. Okay, at 0 degrees. This reaction is endothermic. Okay, and here's the heat of fusion is this amount right here. We won't worry about the exact number, but you can write it as energy plus ice will give me liquid water. Okay, now if you add heat or energy, the reaction will move to the right. You make more water. Okay, now if you were to take away heat, you cool down the water and you make ice. That makes sense, right? Okay, and here's another reaction. This is an exothermic reaction. You see the negative here. So this is plus heat or energy. So now if you add energy, the reaction will move to the left. Okay, and if you take away energy or heat, it'll move to the right. All right, so we're going to apply Le Châtelier's principle and look at the reaction quotient. And we've already talked about using this to some degree, but be more specific now. So what we're going to look at is what happens if you have reaction, too much reaction, reactant, too much product. That means Q is different than K, how it's going to shift. And we went over these here. Okay. So let's go over an example here. So here's a chemical reaction, and you can write the reaction quotient. And remember, this is at any time, not necessarily equilibrium. When it's at equilibrium, Q is equal to K. What will happen if PO4 3 minus is removed? So if you take this away, what are you going to do? You're going to have less reactant. So you're going to have less this guy up here. So the reaction is going to go to right. So in this case, Q is going to go down. So in this case, Q is going to decrease. Right, because there's less product. And so the reaction is going to shift to the right. Okay. All right, so now we're looking at the same reaction, or a different reaction. Here I have phosphoric acid plus hydroxide gives me water and phosphate. And this is an exothermic reaction. Okay, what would happen if the system is cooled? So cooled means you're going to take away heat. All right, so essentially what you could do is you could write heat up here on top, even though it's not part of the reaction. And if you remove this, Q is going to go down and the reaction moves to the right because there's less heat. Okay, then this is the final slide of this. Following our equilibrium constants for reaction acids and water, Ka, which reaction proceeds furthest to product? So K, we'll call it Ka because it has acids, is equal to product over reactant. Okay, so there'll be a lot of product, so this number has got to be very large. And so you want to have the number that has the largest exponent. Okay, so if you look at these, it's either going to be 3, -5, -10, and -3. So these two, this one here says there's hardly any product at all. I mean there is product, but it's 10. It's like 1 out of 10, 10 to the 10th. This was like 1 out of 10 to the 5th. These guys are similar, all right? So they both have the same exponent, 10 to the -3rd. So it's the number in front that determines how much a product which one is larger. So it's going to be D. So it's going to take practice as you look at these and try to think of them physically. Don't try to think of it in terms of any kind of tricks, And the next slide, we're going to be doing some specific examples and problems using equilibrium, and I'll be applying what we talked for this slide. All right, we're off to the next one.